Hi everyone, good afternoon. This is Meraj Rubayat Kamal. I'm currently doing my PhD at the University of British Columbia, Okanagan. And today I'm going to discuss about glass fiber reinforced concrete. So the topic is development of an eco-friendly glass fiber reinforced concrete using recycled glass as a sand replacement. So this is basically the outline of my presentation. So I'll discuss some background, then I'm gonna discuss our experimental program, then we have the test results, and at last discussion and conclusion. So background, we know concrete is the most widely used construction material on earth, and in 2021, 30 billion tons of concrete was used. And aggregate is the primary constituent of concrete, and it can take up to 60 to 90% volume of concrete. So that's quite huge, and we know aggregate production and its transportation, it contributes significantly to the disturbance of the ecological system, and it also causes the depletion of natural resources. So if we can substitute the aggregate with some waste or recycled materials, we can definitely conserve the natural resource, and it also has the potential to lower the carbon footprint of concrete, of the virgin concrete. That's why in our study, we are investigating the applicability of using a poraver. Poraver is an aggregate which is made of 100% recycled glass or waste glass. So we are preparing lightweight glass fiber reinforced concrete, or we can call it glass fiber reinforced cementitious composite because it doesn't have any coarse aggregate. But traditionally, it is actually called glass fiber reinforced concrete. So now, what is it? So glass fiber reinforced concrete, so as I said, is GFRC. It's basically a cement-based composite material which is reinforced with glass fiber, usually the alkali-resistant ones, and it's actually made by combining a mixture of cement, then fine sand, then it has water, then polymer, and some other admixtures, and obviously glass fibers. And it has different uses, but it's primarily basically used for producing lightweight yet strong architectural cladding panels. Like it is also used for the countertops or window surround elements, and sometimes it's used for the fireplace mantles. And GFRC was basically developed in 1970s, and since then it is being used as a cladding material. Now, what is the advantages or disadvantages of GFRC? So as I have mentioned before, GFRC has an excellent strength to weight ratio because it has the glass fibers which kind of works like a steel fiber, or the steel reinforcement. It provides the tensile and compressive strength. But since glass fibers are pretty light, so it has a good strength to weight ratio, and the GFRC is lightweight. And some researchers have found that GFRC is also durable and it has good moldability, so we can make it in any shape if we want. But as it has some disadvantages, so GFRC are usually prone to impact failures, and sometimes it's more expensive than traditional concrete, and is not suitable for the load bearing purposes. Now, what is poraver? As poraver is the aggregate that we are using for our GFRC. So poraver is a lightweight aggregate, as I have mentioned. It's made from post-consumer recycled glass, and it's actually made from 100% waste glasses. So the glass granules, which are not further used for producing a new glass, these glasses are used for making poraver. And regarding the production process, actually the broken glass is first finely crushed, and then it's blown in a rotary kiln at a higher temperature, which forms the spherical shape of the poraver granules. And again, poraver is used for basically lightweight concrete and cladding panels. Sometimes it's used for plasters and also tile adhesives. I'll show you the experimental program of our study. So in our study, we made three types of concrete mixes. One with 0% pour over, or we are calling it a control concrete. Then we had 50% sand replacement with poraver, and we had 100% sand replacement with poraver. And the sand that we replace is silica sand. Usually GFRC are made of silica sand. So silica sand, I guess we all know about it. It contains around 95% of silicon dioxide and usually less than 0.6% of iron oxide. On the other hand, the construction sand, the brown ones that we usually use, it usually consists up to 80% of silicon dioxide. And the silica sand is made from quartz. So this is our three types of mixes, and we compared the mixes based on the unit weight, which is our main focus, then compressive strength, and we did splitting tensile strength, and we also did the durability test in terms of freeze-thaw resistance. And we also did some additional tests on pour-over concrete, like the density, water absorption, flexural strength, and glass fiber content in the concrete. So this is basically an ongoing project. We are still doing some more tests. And here we can see the properties of the two aggregates that we used. Okay, so if you look at the FM, so the silica sand had an FM of 2.2, but the pour-over that we used had an FM of 1.9. And the interesting thing is the oven-dried bulk density. We can see that the silica sand had a density of 1490 kg per meter cube, but the pour-over only had a density of 590 kg per meter cube, which is pretty light. And if we look at the water absorption, the silica sand had a water absorption of 0.42%, but however the pour-over is 28%. I know is a bit higher. And regarding the pH, silica sand had 7.6 and our pour-over sample had 10, so it's basically alkaline or basic in nature. And silica sand we found from ACM is angular in shape and the pour-over is spherical. So this is the comparison of the aggregates. And this is the mix design that we use. So we have three mixes I mentioned, P0, P50 and P100. P0 is the control one with 100% sand. Then P50 has 50-50 and P100 has 100% pour-over. So if you look at the polymer, it's actually 72 kg per meter cube, which is 12% of the cement content, and we had 4.5% of glass fibers by volume. And the super plasticizer that we used is the type F1 high range water reducing admixture. And the water cement ratio, we can see that is 0.32. GFRC usually has a water cement ratio between 0.3 to 0.35. So the mixing process is pretty simple. It's a hand mixing. So first the water is added, then the polymer is added to the water. This polymer gives you the early strength, because sometimes people want the GFRC to cure early, so it gives the early strength. Then on that mixture, super plasticizer, the water reducer is added. Then the cement and sand is added. This like 50% of the cement and sand is added. Then they are adding the glass fibers, which is added little at a time, and the mixture is continuously turned on. So like the glass fiber, after adding all the glass fibers, the mixture is continued for 5 more minutes. So the total process takes around 12 minutes from adding water to the completion of fiber addition and mixing. So regarding the test, so GFRC has some designated tests prescribed by ASTM. So we try to do those tests. So this is the test ASTM C948, which is for thin sections of GFRC. And this is dry and wet bulk density, water absorption, and apparent porosity test. So we did this one. And we also did the test for GFRC content in glass fiber reinforced concrete. This test is called it's a washout test following ASTM C1229. So for this test, two 6-inch by 2-inch coupons are cut from a freshly produced cladding panel, as we can see from the second picture. And then it's washed, then it's dried, and from the dried sample we can measure the amount of glass fiber. We also did the traditional compressive strength test and also the splitting tensile strength test of the cylindrical GFRC specimens. So in the third picture, we can see the sample after tensile test, and in the fourth picture, we can see the sample after compressive strength test. And we also did a specific test for the GFRC, which is called the flexural properties of thin sections of glass fiber reinforced concrete using simple beam and third point loading. That is ASTMC 947. This is basically a 4-point bending test. And finally, we did the freeze thaw test at ASTMC 666, and we used procedure A. So if we look at the test results, if we look at the compressive strength, so P0, P50, and P100. So P0 gave us a compressive strength of 35 MPa. With P50, we got around 27.5 MPa, and with P100, we got around 21 MPa. So we can see the strength is gradually decreasing with the addition of poraver. But if we look at the unit weight, so the P0, it had a unit weight of around 1900 kg per meter cube. But the one with P100, as we can see in the third picture, it had a unit weight of only 1300 kg per meter cube. So we can see that the unit weight for the third one, P100, is at more than 30% less than the control one. So we are making GFRC, so we want to make it lightweight as far as possible. So with 100% poraver, we can reduce the weight more than 30%. So this is the result of the compressive strength and unit weight. Then we can see the splitting tensile strength. So the control one gave us around 6 MPa, 5.7 to be exact. But with 50% poraver and 50% sand, it had the highest strength. It's more than 6 MPa. And with P100, we are getting 4.9 MPa, so which is not bad. So P50 had higher strength because it had like two types of sands. So the one with poraver, which are fine sands, and the silica sand, which is coarse. So I guess it had a good aggregate interlocking. That's why it had a better strength than the other two. And if you look at the freeze thaw durability, we actually check the mass after 300 freeze thaw cycles. We can see that none of the samples had any weight loss after 300 cycles. So P100, we can say that P100 with 100% poraver performed as good as the control concrete in terms of freeze thaw durability. So these are the additional tests that we did on only the poraver concrete. So we got a flexural strength by 4-point bending of 5.2 MPa, and the bulk density dry basis was 1280, wet bulk density was 1460, and the water absorption is 14%, porosity 18%, and the fiber content from our test we found is 4.4%, 4.44 to be exact. So regarding the discussion, since I have mentioned GFRC are primarily used for architectural cladding panels, so we want to reduce its weight. So further weight reduction is beneficial, and from our study we found that with poraver we can reduce the weight more than 90%, and we are not compromising much on the mechanical properties, and we are getting very good durability properties. So we believe this study will provide a promising view to develop an eco-friendly GFRC with recycled glass as sand replacement. So as I have mentioned, this is our ongoing project. So we plan to do some other tests on our GFRC, like we'll do more material characterization tests on both poraver and silica sand. Like we want to do the ACM, EDX, and also particle size distribution, and also XRF for these two samples. We can have a better idea. Then we'll also compare the samples based on flexural strength ACM and EDX, the concrete I mean. And since it's the GFRC, we want to do the fire test. We want to find out the fire rating, and also we're planning to do the impact test on the concrete. So these are the references that I used in this presentation, and I would like to acknowledge MyTex for providing the funding, and Clad Surface, they also gave us the funding. That's the industry. So thank you everyone, and if you